Okay.
Eliminate this.
Okay. Our next talk is by Francesco Calogero, and the title of the talk is Recent Identifications of Explicitly Solvable Systems of Nonlinear Ordinary Differential Equations, Difference Equations, and Other Recursions. Please begin.
But how do I move my?
But so you just you may just tell us when to move to another page.
I don't see how to.
No, you cannot move now.
You cannot move by yourself. You just say us, and we move below.
Okay, well, so the.
But please note that our pages are now it's okay. Pages inside the screen. Okay.
All right, so best wishes to Andrei. This is talk is identification of explicitly solvable systems of nonlinear ordinary differential equations, and
Okay.
I will discuss this equation here. Can I enlarge this, or and how do I move? Almost all the results here have been obtained in collaboration with Professor Farin Payandev from the University in Tabriz, Iran. Do I go on?
Well,
You move the transparencies.
yes. The next page.
Oh, I see, page by page. Well, I wanted to say some words about the meanings of the term solvable. There are, if you want to study equations or system of equations, there are in a way two approaches. One I call the Poincaré approach, and this is you are given a system of equations and then you try to find the properties of the solutions. Maybe equilibria, behavior near equilibrium, asymptotic behavior, special solutions, and things like that. And the other approach, which I call the Poincaré approach, is instead you are looking for special systems which have special properties. So maybe they feature analytic solutions or some property like that. So in the first part of my talk, I will use mostly the Poincaré point of view. So I will try to find system of equations that are in some way treatable. And in the last part, instead, I will take a very general system and try to find the solutions of this general system. And solvable maybe mean that you actually find the solution explicitly, or that you show that the solution can be obtained by algebraic operations. Next, transparency. Do I do this? No. Okay, I just remind you of a property of system of ODEs, and the property is for system of ODEs. By the way, do you see my arrow? I don't hear.
No, we cannot see your error, unfortunately.
Well, then in equation 2 is now the equation, and the right-hand side is this function f, and I assume that this function f is homogeneous of degree r. For these equations, there is a trick that is actually the subject of this book of mine of some 15 years ago. And the trick is the following. You go from the dependent variables xn of t to the dependent variables yn of t by transformation, which is written in the first part of equation 4. And that transformation changes both the dependent variables and also the independent variable. You go from n to tau. And then you have this transformation for this type of systems has the property that it transforms an autonomous system into an autonomous systems. So you go from equation 2 to equation 5, which is still autonomous for y. And because the dependence of y by t is through this function tau, which is periodic in t, this system generally has periodic solution. In fact, it may even be isochronous. Maybe all the solutions may be periodic. Of course, if the corresponding function x had some property. For instance, if this equation had chaotic solutions, then if you have a periodic dependence on it, which travels on a periodic solution, it's of no help, because this solution then will just travel in the complex tau plane, as you see from here, on the solution of the other function, which is the x of tau. But generally, for many systems, this is interesting, allows you and it makes interesting to study systems that have algebraic solutions, and then eventually the new systems will be periodic. This is the case for systems of first order, and this is the case for systems of second order. Do I eliminate this?
Well, the next.
But how do I go to the next?
Just say that the next, and I will switch.
No.
Oh, Francesco, you should just say us next page, and we will do this.
Okay. So now yes. Okay. Now I'm reporting on this system, which is written on top of the page. It's a paper by myself with Conte and Levras, and it studies this kind of systems. It's a very simple system, but also very, very classical, and it has been studied for centuries. It's a system of only two coupled first order or ordinary differential equations with the right-hand side that is quadratic in the variables, and it contains therefore 6 arbitrary constants. So see this 6, Cn1, Cn2, Cn3, that's value. So you have 6 constants. And the purpose of this paper of ours, which is already 2 or 3 years ago, is to find cases in which these equations are algebraically solvable. The trick to do that is in this approach. First, you try to find a canonical form of this system of equations, and by this linear transformation, it can be shown that almost all these systems can be reduced to this canonical form, which is equations 13, A and B, and the canonical form has only 2 constants, A and B, which are then connected with these original C's and this transformation. And then the result of this paper is to make the following statement, that if this constant A and B, there are 3 forms here, have this particular form. Let's just look at the first one, the others are analogous. If you look at equation 14a, A and B have these forms with n integer, an arbitrary positive integer, and q, an arbitrary non-vanished complex rational number. So there are this restriction. Then the statement is that the solution for this system Y is algebraic. You can obtain it by algebraic operations. And then, of course, also the solution for X you can obtain by algebraic operations. So these are the type of results that is contained in this paper. There are also some special cases, which are here below, 15, if you move ahead. Yes, well, and then let me just point out this result here, which I cannot see because it's covered by this thing here. I just don't know how to take this away. Can you move my screen No, the next page, next page.
Yes, okay.
But I don't see it because the right part of my screen has some, oh yes, okay, this is now better, all right. Okay, now this is, can I go to the, okay, well, we jumped ahead. The page below was just to show
Do you
you
want the previous?
this paper by myself, Comte and Legrath. We found an example of a Newtonian equations. Can you go back to the previous page? Yes, below. Next page here. Yes. Okay, all right. Now look at equation 17 here. You see, this is a Newtonian equation for just one variable with the exponent on the right. The exponent that we found as these two classes of values, either k is n plus 2 over n minus, or k is minus n minus 1 over n for an arbitrary positive integer. And then this equation has algebraic solutions. This result apparently was not known, although, as you know, Newton discovered this equation some centuries ago. And this is the very simple case of a single Newtonian equation. This implies then, by making this trick, because the right-hand side here is homogeneous, of course, you have only one power, that if you make that transformation in the case of a second-degree equation, you get what is down equation 18, written here. Omega is an arbitrary real parameter, and then this equation is isochronous. All its solutions are periodic with this, with some multiple of this period t, which is written below equation 18. So this is what is written here. N is an arbitrary integer. So nice result is the discovery of a new class of Newtonian equations, just Newtonian equations for one variable, which are, well, this is Newtonian. This is not quite Newtonian because it has this part with the velocity here. And also, these are really two coupled equations because we are now talking about complex equation because you have this imaginary term on the right-hand side. Let's go ahead, if we can. So the explicitly solvable case, this is now a paper in collaboration with Farin Payande, and this paper we treat the same system as before, but now it's not homogeneous on the right-hand side. So it is the general equation with the polynomial, with two polynomials on right-hand side for the two equations on the right-hand side. And the approach used here is different from the one used previously. We don't reduce to a canonical form. We found a system that can be solved explicitly. It is this for the variables y, and then let's go ahead because yes, well, the trick is to relate this original system 19 to a system 20, which you can solve exactly. The 21 gives the exact solution, and then one can show that if the coefficient of equation 19 are expressed in terms of the parameter of the other system, the solution can be obtained explicitly. It's written below. Let's go ahead. But that implies a certain constraints on these coefficients. Let's go ahead. These are the explicit expression of these coefficients. Next slide. Yes, this is the inverse problem to express the parameters in terms of the coefficients. The coefficients in terms of the parameters is easy. We had before. But then it turns out that in order to be able to express the coefficients of the equation, the parameters of the solution in terms of the coefficient, you have 4 constraints. So this kind of systems of that time that can be solved require these 6 constraints, which are the equations 26 from A to B, and then the solution is explicit, it's written explicitly below. So here we are treating this system with a general polynomial of 2nd degree in the right-hand side, 2 equations with 2 polynomials. And we find that if the 12 coefficients of this polynomial are restricted by 4 conditions, then the solution can be found explicitly. And the 4 conditions are this one. Let's go ahead to the next thing. What time do I have to finish? Okay. Now, this is now another solvable model. This is a homogeneous polynomial on the right, again, a collaboration with Farin Payande. And this is now a cubic polynomial on the, again, 2 equations coupled, but with a cubic polynomial in the right-hand side. So in this case, you have 8 coefficient C, and the system has an isochronous variant, which is this equation, but this is isochronous only if the equation for, if 33 has algebraic solutions, then 34 will be isochronous, all solutions will be periodic. And of course, this 34 means a doubling of equation if you want to stay with real variables. And this again, the trick here is to relate this to system that you can solve. And the system that you can solve in this case is a system with 7 parameters. And so this system had 8, the new system is 7. And these are the expression of these parameters, these 8 parameters in terms of 7 parameters, which are in these equations. And well, that is the, you can go ahead because this is the essence of this paper is this result. The form of the solution in this case is a little bit complicated. The solution is given by a linear relation in terms of this, if you look at equation 37A, then x1 and x2 are given in terms of these 2 variables, y and w, and by linear relations. And then y is a very simple function, you see 38, equation 38, but w is a bit more complicated because it is u times w times y, as you see in equation 39a, and then u is the solution of this algebraic equation. It's algebraic if this parameter lambda 1, lambda 2, lambda 3 are rational. And these parameters, if you go down a little bit, you will see how you obtain them from the original parameters. Next transparency. And no, I think the previous one, well, anyway. I think, yes, this is this formula 39E, which gives the exponents in 39B. And these numbers U, the 3 numbers U, are the solution of a cubic equation. So you are reduced to algebraic operations. 39, solving 39B is, of course, more complicated. It will be algebraic only if the 3 lambdas are rational, which requires that this solution should have rational solutions. So this is the type of results that one obtains. One studies the general equation with the cubic polynomial homogeneous on the right-hand sides and find some classes of these equations which have solutions which can be controlled in this sense that I've told you. Some of them you can even say that the solution are really algebraic, and then you can also modify them so that they are isochronous. Don't forget that this system in general for an arbitrary assignment of the two polynomials have chaotic solutions. They are very complicated. They are not simple. Let's go to the next talk, because I would like to spend more time on this, because this is a yes, thank you. This, as you can see here, is a paper that has been submitted 3 days ago to Qualitative Theory of Dynamical System. Again, a paper by myself and Farin Payande. A few months ago, we put preliminary results on the archive. And this is now a little bit of a, from some points of view, the results are very simple. From some point of view, there is a little bit of a new approach. And just, okay, just let's look at the equations that we are dealing with. This is the equation 41a. Now we are looking at the property of a general class of equations. And this is, as you can see, well, it's fairly general. If you go ahead, it is a system of an arbitrary number of ODEs with right-hand sides, which depend on this. Of course, the equations are autonomous. There is no explicit time dependence. And then these functions, which are on the right-hand side, fm, fm below and m above. M, this is these functions on the right of 41a are homogeneous functions, not necessarily polynomial, just homogeneous of degree m. And m, for simplicity, we assume that it is an integer because we want to have equations which are univalent. Most of the results would be true if m were not an integer, but it can be an integer of any positive or negative. And let's go down to the expression of this fm, page, next page, the right-hand side of this equation. Yes, this is it. The right-hand side is written up here, the equation up, thank you. No, more up, before. Yes, 40. This function f, as I told you, has to be homogeneous of degree m. So it satisfies the equation 41b. So you can express this in this sum, in this form as a sum, because then you see this is automatically isochronous of order m. But this sum can have an infinite number of terms, the coefficient here, because it can be an infinite series. We always assume that this function is univalent, but it could be an example of cases in which there's an infinite number of terms when written in the form for 2. If you go a little bit down, is when you have this function fm of all the variables, go down yes, a little bit, is just the ratio of two polynomials. The polynomial above is homogeneous of degree mn plus, and the one below is homogeneous of degree mn minus. Note that, and then go down a bit. So these are the polynomials which are written in 43b, above and below. And now the condition is, of course, that the polynomial above minus the polynomial, these are homogeneous polynomials, of course, above and below. And the difference of the degree mn plus and mn minus should be this m. So if you go down with the equation that we have next equation. Yes, this is the condition. So we are looking at the class of system which is very large because it's an arbitrary number of equations. And the only restriction for the moment is that the right-hand side be homogeneous of a degree which is also arbitrary m. It can be any, but m, we assume it's an integer because otherwise the equation will not be well defined. All right, now let's go to the main result. The main result is very, very simple, but it corresponds to taking, go back, yes, yes, okay. This is, yeah, main finding, next page. Main result is, yes, here, stop here. This is again the equation written, this fairly general equation with the property to be isochronous. I repeat, written in this form, this equation can have an infinite number of coefficients, even when, for instance, it's a ratio of 2. And then the statement is that this equation has a class of special solutions, which are very simple, and they are written here. This is equation 45a, and probably this was known that this solution existed, because it certainly is known when m is 2, namely the right-hand side is quadratic, and then this is just 1 over 1 plus kt. K is a constant, and the solution, and these are, of course, the initial data. And if m is 1, then the solution is a bit different. So this is the statement. Now, the new aspect, so to say, is to look a little bit seriously at this solution and see what are the conditions in order that the solution exists. And then you find that you can express explicitly the condition in terms of the initial data and all these parameters C. So this is then the condition. This is m is different from 1, and this is m equal to 1. Let's look at the more general case. It is this one. So you see there are n constraints. These n constraints are on the n initial data, but actually it's only on the ratio of the data. And then you have a free parameter, which is this k, and then you have this very large number of coefficients. So the statement is that this general system feature has this solution or this class of solutions, provided there is this condition, which is a condition on the initial data, on the coefficients, namely on the equation, and then you have this free parameter k, which can be determined by this equation. And you may also note that these conditions are linear. If you take an arbitrary k, so they are linear in this coefficient Cm. So you can, and these are n conditions. So you can simply solve them for n of these conditions, of these parameters, and you can do that explicitly by just solving linear equations, linear algebraic equations, and then you find a class of systems which has these solutions. Now, don't forget that in a case which is of great interest and study is the case in which n is just 2. And in this case, you just have just 2 conditions, but k is arbitrary. So actually you have just 1 condition on the system. So let's look at a few examples for the n equal 2 case. So for the n equal 2 case, we take this system. You see, it's now, I write it in this way. This is, you have just 2 coefficients. So the sum here is just on this index m, which takes an infinite number of values in principle. And then it's homogeneous of degree m. Look at 49, the equation, and that's all. So a very large class of homogeneous equation of order m, but only in two variables. And then the statement is that the solution is this one. And what are the conditions? Let's go ahead. This is still for the general class. The conditions are written here. It's the same as before, but just for n equal 1 and 2 and 1 and 2. And now you can just take the ratio of this for n equal 1 and n equal 2, and then you introduce the ratio of the two initial value. And so the statement is that if the ratio of the two initial values for this general system satisfies this formula, because you have taken the ratio here, then the system is solvable. And I will give you a specific example for the case, for this case n equal 2. This is the general case n equal 2. You see here you have in principle an infinite sum. So let's take the very classical system in which you have just this equation. Now, this is now a polynomial. Example 31155a is this very, very classical equation, which has a second degree polynomial on the right hand side. And so how many coefficients you have here? You have, I think, n goes from 0 to 2 and n goes from, so you have 6 coefficients, as we had already seen before. This equation has 6 coefficients. And then the statement is the following one, that this equation has a solution of this very simple form, Zn of 0, 1 plus k to the minus 1. If there is only one condition, because see, the number of conditions is big N, but if k is free to be computed from this formula, you have only n minus 1 condition. So only one condition, and the condition in this case is 55D, which is written here. And if you go a little bit ahead, you will see that 55 in this case is a the cubic equation. I don't know. Next page, tell you, you can see. Or I think I just let me go back to a page back because you. Thank you. Yes, down, down, down. Yes. What degree is this equation? You can see from it. This is an algebraic equation for this quantity R, and it's a cubic equation because the highest degree is R cubed when m is equal to 2. So you have the generic cubic equation, which depends on this 6 coefficients. If the initial data satisfy this cubic equation, which has 3 solutions, so there are 3 classes, 3 groups, or 3 values for the ratio of the 2 initial data, then the solution has this very, very simple solution. And these are the type of results. Now, we can look quickly at some other example. Let's go ahead with the, yes, this is, there was, I think, an example 2, where this is a polynomial of 2nd degree on the right-hand side, and the class of solution is this very simple 56a, and polynomial of 4th degree. 56b is the solution in this case, which is to the power s minus 1/3. Note that in this case, the solution is, it has branch points, but when you then make the extension to the periodic case, still the solution will be periodic, but it will depend when you go round in the complex plane, whether it is the branch points are inside or outside. This gives a slight difference of period, but the solution will be isochronous. And the condition in this case, this particular case, is just this one. We are always with 2 variables. You just have one condition on the initial data. And in this case, it's a polynomial of 5th degree. So in this case, you cannot solve it explicitly. Let's go ahead, another case, which is this one, where the equation is now of degree, what is it, 1 above, 2 below. So it has m is equal -1. In this case, the homogeneity degree is -1. You have two polynomials. I think you have 10 coefficients in this case because you have 2 above and 3 below, and then you have two values of n. So this is a system with 10 coefficients. Of course, one can be factorized. And then let's go to the next slide, the next page. Thank you. In this particular case, the condition, if you look at, this is the condition. It's written here, running one, and the condition just, if you just take the ratio of these two, condition 57C, by the way, the solution in this case is to 1/2 because m was -1. And this is the algebraic equation. In this case, the algebraic equation is of degree 4 for the parameter r. So again, I repeat, for this class of equations, if the two initial data have the property that their ratio satisfies a certain algebraic equation of degree 4, which is given here explicitly in terms of the initial data, then it has the solution and the value of k will be given by this formula. Of course, vice versa, you can instead choose arbitrarily the initial data, and then you can find two coefficients of the equations, two of these 10 C's in terms of the orders. And in that case, you only have to solve a linear equation. All of this is, from a mathematical point of view, rather elementary, but for applications, it seems to be a bit of a breakthrough, because if people who are interested in these equations to model whatever they model, epidemics, chemical reactions, population evolution, or things like that, they want to know how is the behavior if in terms of the parameters, and this allows you to find special cases in which, by controlling either the initial data or the parameters, you get a very simple behavior. There is another example here. If we can go ahead to, yes, this is an equation instead of degree, homogeneity degree 1, because you have a polynomial of second degree above and a polynomial of first degree below. And this equation, so this is a very simple solution, and the condition is, in this case, it amounts to again a non-solvable equation of degree 4, which is written here for the ratio of the two initial data. Let's go, I had some examples with n equal 3, just to give you an idea. So for n equal 3, these are the general formulas that you have. And in this case, you see n is 3. The number of constraints overall is 3. Because k is free, you have two real constraints. So if you look at the constraints only on the initial data, you have just two ratios of the initial. So let's go a little bit below to see this equation. All right, no, this back, yes. All right, this would be the constraint, the two constraints on the ratio. In this case, I had the 1 of 0, the 3 of 0 is the 2 of 0. The ratio of the two first initial data to the third satisfies this equation. And of course, what is the degree of this equation depends on the right-hand side, which depends on how complicated is this equation. There are several examples. Let's go ahead. This is, we can look at this. There is one example here, but which again has a solution of the simple type. Then you can, because you are dealing here always with equations with homogeneous right-hand side, you can use this trick, which I mentioned to you before. This is a variant. In the previous case, I used the trick with I omega, but here is more general with eta. And so, and moreover, you can shift the variables. So you can go from homogeneous system to non-homogeneous system. And in general, you get as many as n+1 free parameters. You have this parameter in 66A, you have this exponent, this number eta, the exponent, and then you have begin shift of the variables if you have begin variables. And so this is the way to go from system with homogeneous right-hand side to some instance without homogeneous right-hand side. Again, very elementary operation from a mathematical point of view. It enlarges the class of solutions in this way. Maybe I have some examples of this case if we go ahead. I think we are near the end of this paper 22. Yes, okay, so this is the proposition that tells the result for this more general case. So the general equation that you treat is 70A. Now you see you have an equation which is no more homogeneous. You have all these parameters Z bar of n. And let's go ahead to look at the examples, which are ahead, yes. Well, this is just one example in which you have above a polynomial of degree 2 and below a polynomial of degree 1. And then you have this term. So this is the right-hand side is homogeneous of degree 1. And then the solution in this case looks like this. You see, it's an explicit solution. The solution that we are trying to see which systems of this kind have the solution, and then we find that in order for this to have solution, there must be just these two constraints which are written here. Because we are still doing now here with two equations now. And I don't know, what do we have more here? Let's go to the next. Yeah, yes, the next is just one example, a little bit different. Yes, well, in this case, it's one page and the other, page 70. 73 is a ratio of two polynomials, and 72A is not a ratio of polynomials, just a polynomial. So this is homogeneous of degree -1 and of degree 1, the polynomial of degree 2 above, but with the denominator, which is a polynomial of degree 1, and the other one is just a polynomial of degree 1, which you don't see now, but it is 73A. And again, these are the conditions that you have in order that a special case we can go ahead is the so-called asymmetric May-Leonard model, which is an example of this kind of equations. And so we can go ahead to, do you hear me? Yes. And so the homogeneous May-Leonard system is essentially this one, and it's a special case of those that we treat. And you can get these solutions, which in this case, because the homogeneous, the symmetric May-Leonard model, it's not homogeneous, but it can be obtained by this trick. So the degree is essentially quadratic, but these are three dependent variables, three equations for quadratic right-hand side, up to the fact that with the trick you can also get terms of this type. So this is the asymmetric, much studied this model, but I'm not aware if there are many papers whether it was noticed that this solution existed, but in particular whether it was noticed what the conditions are on the initial data or on the coefficient C in order that this solution exists. And this, in this case, because we are talking about a system with 3 dependent variables, 3 equations, there will be just 2 conditions or 2 conditions on the ratio of the initial data, for instance. Let's go ahead a little bit. I just want to see what else we have in this. Yeah, models. Well, this is models with periodic solutions. If theta is I omega, then you have the cases in which the solution is periodic. These solutions that we find is periodic. And of course, not all the solutions of this system are periodic, but all the solutions which satisfy these constraints, which involve, you see, the new approach here is that you put constraints which constrain the equation, namely the coefficient of the equation and the initial data. And you can play around with these constraints to have them, and the constraints on the equation are always very simple because they're linear. I think I am rather at the end, but let's go ahead. I don't think I have anything more here. Well, these are some additional examples, but I think you have understood the philosophy. So if I will not stop, but say just one last thing. And the last thing is that this same approach can be used for recursions. That is not differential equations, but recursions. Something very similar works there. The solutions are a little bit more complicated, but can be given in completely explicit form. And in fact, I had intended to also include this in this presentation, but then I decided, well, the results were not yet in completely nice form, so I didn't include this. I will include this result in my talk in Yerevan, which will be in October. I think I should stop now. I don't know how much I was doing with time, because and if there are questions, I will of course be happy to.
That's okay. Thank you very much. And we have a few minutes for a few questions.
Yes. Well, while we're waiting for the questions, I wanted to give my best wishes to Andrei.
Okay, thank you very much, Francesco. Thanks a lot for the nice talk. And okay, thank you.
So okay, if no questions, then we proceed to the next speaker. And
may I ask a question?
yes, of course.
I mean that your equation, which has quadratic, homogeneous quadratic equation, all of them like explosive type solutions. One.
Yes. You see,
how do you use this form of solution in?
You have a system of right-hand side. And this system is very rich. If you have a general system, even if the right-hand side is quite simple, even if it is just polynomial, both are polynomial degree 2, the system is quite rich. So those that we identify are special solutions which exist if you have some limitation either on the coefficients or on the initial data, combine the two together. There are other solutions, of course, including solutions which are not only that it's fluid, but they are chaotic. So it's a all these systems are systems that have very complicated solutions. But what we do is identify some conditions that then imply that the solution is instead very simple. And this condition, what is a little bit new is that we take conditions not only on the equation, namely on the coefficient of the equations, but both on the coefficients of the equation and on the initial data. And if you combine the two, you can explicitly say that if the coefficient of the equation and the initial data satisfy some constraint, very simple. It's linear for the coefficient, and it's also simple for the initial data. Then there is a solution which is simple. But the system is complicated. These systems are very complicated. For this very simple system with two equations and just making it go round, I think Paolo Santini, who will talk tonight, and Griniewicz have shown that the solution can be extremely complicated. Griniewicz is present, I think. No, not Griniewicz, Griniewicz. So these are systems that are, of course, very present in many applications, in many fields of applied mathematics. But they can have very complicated solutions, chaotic, explosive, they have equilibria, behavioral and equilibria. So they have been studied for many years in many contexts. And now, of course, they're even very popular because they can mimic, they can describe epidemics. Our approach is to find some special simple solution of this equation and see what conditions are required in order that these solutions exist. The conditions involve both the type of equations, the coefficients of the equation, and the initial data.
All right, thank you.
Okay, and I want to ask also a short question. And are some of these systems Hamiltonian? Is it possible to? Are some of these systems Hamiltonian? Is it possible to formulate solvability in Liouville sense of existing commuting conservation laws?
But yes, well, some of this is Hamiltonian. What was your question? Whether they are
is it possible to formulate solvability of these systems in Liouville sense as existing of commuting conservation laws?
Well, you know, we are looking, I have to repeat, we are looking for special solutions, and the special solutions that we identify require that some conditions be satisfied both by the equation and by the initial data.
Yes, I see, but maybe some of them do.
Observed quantity is a property of the equation, of the coefficients of the equation itself.
Yes, I see.
Associated with special solutions.
Okay, thank you very much. Thank you. Okay, we stop.
Thank you,
Can I
Francesco.
just ask a question?